Right, well, let's get started. What I'd like to do is just have everyone do a brief introduction to themselves, and then we'll end with Edward, and then Edward can continue directly into the presentation for today. So my name's Paul Borrell. I'm the CEO of Daedalus, and we try to make the world safe for transactions. Pat, you're next. Go ahead.
I'm Pat Helland. I work at Salesforce. I've been building distributed systems, databases, and causing trouble since 1978.
May, you're next on my serpentine.
Sounds good. I'm May. I'm a professor at Princeton, and I work at the intersection between programming languages and distributed systems. My primary purpose here is to ask, did we really need time?
Andy.
My name is Andy Helland. I happen to be Pat's brother, as it turns out, but my background was in distributed storage for a period of time, and also a lot of work in signal processing.
Excellent. David Shortbeard, you're next.
Professor David LaRiviere, University of Illinois. I deal with algorithmic trading, both the algorithm, software, and hardware stack.
Excellent. Kevin, go ahead.
I'm Kevin. I work on synchronizing time so that it's more accurate than the best case communication latency.
Ken, next.
Hi, Ken Berman, Distributed Systems, Cornell University.
Okay, Dugan.
Dugan Hamrick. I work with Stephen Wolfram as a research coordinator.
And Sebastian, you're next.
I'm Sebastian. I'm doing software engineering infrastructure. I used to do optical networking. I'm based in Switzerland.
Wonderful. Dave, Lucy. Dave Longbeard, we call you now.
David Lucy. I also work at Salesforce. I've been building large-scale networks, and both LANs and WANs for the last 30 years.
Excellent. Martin, you're next. Welcome back, by the way.
Hi, Martin Lostro. I recently pivoted out of academia, where I developed the reactor model and Lingua Franca. Edward is my PhD advisor, and now I'm the CEO of Kronos.
Okay. Anjali, go ahead.
Hi, I'm Anjali Singhai Jain, and I work at Intel as a network architect, and I was involved in the design of the IPU that's deployed in Google Cloud. And I'm here just in time to listen to all the good stuff.
Excellent. Ahmed, you're next.
Ahmed Baigawi, I work for Meta, and I'm the architect for the precise time deployed in our data centers.
Let's go circle back to Edward. Please introduce yourself. You can have a much longer introduction if you'd like. And then let's proceed with the meeting. The recording is on, and looking forward to this. Thank you.
Edward. So I'm Edward Lee. I've been at Berkeley for a really long time. My focus is on cyber physical systems, which means that I'm really only interested in computers that interact with the physical world, where for the benefit of May, time actually matters sometimes. So I'm going to do something a little bit experimental here, and I'm going to be completely PowerPointless and show you some stuff using some software that is actually, I'm kind of using a little bit of a experimental part of our software framework, and part of the reason here is that I'd love to get your feedback. And, I'm using stuff that is relatively immature, and I'm going to walk through a bunch of examples that I think are probably going to create a little bit of discussion. So let's just start right into it. So let me see if I can share the right screen and get this off and running. Okay, so you should be seeing a very, very boring Zoom window. So I'm going to use this Lingua Franca system, which you can find out about if you go to just lflang.org. But I'm using a part of it that is relatively immature, okay? It says, right here in the documentation, distributed execution of Lingua Franca is at a fairly early stage of development. And I'm going to use a particularly experimental part of this, which is a coordination mechanism that we have been experimenting with and frankly learning a lot about what we can do with it. It's a very efficient decentralized coordination mechanism. So distributed programs are interacting directly with one another and sending messages. But by default, these messages are time-stamped, and efforts are made to handle messages in timestamp order. Okay. So let me launch right in with a very simple example. So let's see. This is Visual Studio Code. Okay, and we have a plugin for Visual Studio Code that takes a Lingua Franca program. This is a Lingua Franca program in this file. It's specifying to use the decentralized coordinator. And it's a very simple illustrative example that I'm going to create a few different variants of. But this is a distributed system that maintains a very, very trivial, this is the world's smallest database. It has exactly one integer record, which is a bank balance. Okay, so apologies to those of you who do databases. This is embarrassingly small, but that's what it is. Okay, so there's two instances of an account manager here. Okay, and in this very first version, the logic of the account manager is extremely simple. It's shown right here. There's two input ports that will receive messages from two simple WebSocket servers. Okay, so you can imagine each of these WebSocket servers, think of them as an ATM machine. Okay, and the ATM machine just happens that, you know, the user interface is developed in this way where it's using a WebSocket connection and HTML for the user interface of the ATM machine. And at the ATM machine, a client can deposit money, in which case a positive integer will appear on this output, or withdraw money, in which case a negative integer will appear on this output. Okay, so the two account managers receive deposits and withdrawals from all of the systems which may be scattered around the world. Okay, in this case, there's only two of them, but imagine one is in London, one is in Singapore. Okay, and they receive deposits and withdrawals, and they simply they receive them in the form of strings, so they convert them. This is C code in the body of this reaction, so they convert the string to an integer, and simply add that to the balance. Okay, so we can compile this program and run it. So let me get a clean slate here and invoke the compiler. And this is a, let me show you the main reactor. This is a federated reactor, okay, which in Lingua Franca means that all of the top level components become separate programs. They can be mapped into Docker containers. They can be mapped onto remote servers. They can be, you know, scattered around the world. In this case, however, I'm going to just run them all on my machine. But when I compile this program, I get 4 distinct executables, which we can look at. So they get put in this directory called fedgen, and then a subdirectory named after the program, and then a bin directory. So you can see just now at 7:12 a.m. on November 8th, I generated 4 executable files whose names hint at the names of these instances of reactions. In addition, for my convenience, there is a generated script that will launch these 4 programs. Okay, so this is just a bash script that got generated by the compiler, and it launches the 4 programs. If I had specified to map these on remote machines, this generated script would launch them on the remote machines, assuming that I have SSH access into that machine. If I put them in Docker containers, I get a Docker compose that I can invoke to start these up in containers, etc. But right now, I've just picked the simplest possible execution, which is that all 4 of them will execute on my machine. So I can invoke the script. And indeed, it starts up these 4 programs, and the 2 WebSocket servers issue a little message to suggest that I point my browser to their location. So let me do that. I've got 2 browser windows open here, which let me adjust these so that the Zoom window is not quite so much in my way. All right. Okay, got these 2 browser windows. I'll point one to port 8080 on the local host. I get served a very simple user interface. I apologize. I'm really lousy at HTML and JavaScript, so this is also the world's ugliest ATM user interface. And similarly, I point this other browser window to another port, 8081. So now these are interacting with 2 different programs. And I can deposit $100 here. Just submit that, and you can see down here that, in fact, the transaction was recorded on both account managers, A1 and A2, and they both report a balance of 100, and indeed both web pages report a balance of 100. Okay, but now I can deposit another $100 over here, no problem. But here, I can now also withdraw $300. And sure enough, I get my $300 and my balance is now $100. Okay, well, that's exciting. Let me call up my friend over here and deposit $1 million, withdraw $1 million. Okay, well, bank's not happy, right? So, okay, so first of all, I want to point out that a few things about this program. So first of all, I'm using non-default mechanisms in Lingua Franca. So in particular, these little squiggly lines on these connections here are a consequence of this, this statement here that uses a squiggly connection. And what this tells Lingua Franca is, I don't care about time. Throw away the timestamps, okay? So these messages are arriving in non-deterministic order, and they're being handled, but actually that's not. So one way to think about this, by the way, is that this is a Hewitt-Actor model, okay, which dates way back, 1977. All right, these actors are simply receiving messages in the order in which they receive them and handling them in the order in which they receive them. All right. Gulaga did a lot of the formalism for actor-oriented modeling. This is well-cited communications of the ACM paper from, I guess, 1990, okay? For this particular account manager, this policy of doing everything non-deterministically works fine because of what our good friend Pat Helen called ACID 2.0, which is that the updates to the account are associative, commutative, and in this case, idempotence is handled by the Lingua Franca infrastructure because the messages are always delivered exactly once. So we don't really have to worry about idempotence in the account manager, but because I'm just adding and subtracting withdrawals, I am in fact, I have an ACID merge to the database, ACID 2.0. Okay. Another way to think about this particular account manager, it is that it is a conflict-free replicated data type, okay, a CRDT, and that means that I don't actually need to pay attention to time. I don't need to define an order to these events because, in fact, these replicated data types are guaranteed to be eventually consistent, okay? However, the bank's not happy, right? Because you can withdraw an arbitrary amount of money. So let me create a variant of this that has overdraft protection. So I go back to my and let me just open a separate version. It's still throwing away timestamps, okay? But now I'm going to have a bit more complicated an account manager. And in fact, I stuck this account manager. I'm going to use this account manager over and over again. So I stuck it in a library so I can just import it. And let's open it. So the account manager, again, just has a simple reaction to the inputs, but the logic is a lot more complicated. All right. And rather than walking you through the code, let me just show you the documentation for it. So this account manager accepts deposits or withdrawals on 2 inputs, maintains a bank balance, and prevents overdrafts. If the deposits or withdrawals at any time result in a negative bank balance, then one or more of the transactions will be rejected and a penalty will be imposed. Okay. So if one input is a withdrawal and the other is a deposit, then the withdrawal will be rejected if it results in a negative balance. If both inputs are withdrawals, then in one alone does not result. Then if in one alone does not result in a negative balance, then the in2 withdrawal will be accepted and blah, 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 blah. Okay, doesn't matter. This is business logic. Okay. This is what the bank manager decided was the right behavior. All right. So now the merge operation in this database is no longer ACID 2.0. This is not a commutative operation, right? If you, the order in which the operations get applied matters, all right? So let me get rid of accounts 2, and I've actually already compiled all these versions, so we don't have to watch the compiler work. But if I invoke this version and then go to my web page, my 2 web pages, and they're currently disconnected because they were connected to the previous version, but let me reconnect in both cases. So now we're connected to the 2 servers. Now, if I deposit $100 here, I indeed get a bank balance of 100 in both cases. If I withdraw $200 here, that gets rejected. Okay, there's an overdraft message that appeared here. And in fact, I got penalized $30. So that's okay. So that's great. That seems to work just fine. So the problem here, however, is that, well, what do you think the problem is going to be? I mean, you guys are distributed systems experts.
We want to hear your perspective.
Okay. Well, the problem is that depending on the order in which these inputs occur, these two account managers.
May was saying something.
Oh, I'm sorry. May, go ahead.
I was going to ask a clarifying question that was not even related to the question you asked us.
Oh, okay. Fire away.
Where's there must be a response flow that indicates the error to the WebSocket, and I missed where that was.
I apologize. I really am not a user interface designer, and so there's.
Sorry, I didn't mean on the UI. I mean, normally in my head, when I think about how actor models work, there isn't really a response automatically generated to messages that are sent. But here, there must somehow have been one, and I just missed it in the code. My apologies.
Oh, yeah. So the response is sent on this feedback path back to the WebSocket server, and so it flows out over
the display already has. Okay. For some reason, I imagine there'd be like a special notion of having rejected an operation that was separate from just a generic response, but
No.
it seems it's not. Excellent.
Yeah. That there's the Lingua Franca infrastructure here is very generic. It's just handling the message passing, right? It's not. It doesn't have any business logic like the idea of rejecting a message. That's up to you to implement on top of this framework.
Doesn't even seem like you're doing strict RPC. You're just doing messages rather than paired messages.
Yeah, this is not RPC. This is asynchronous message passing. These are socket connections, and it's using TCP/IP, which is how it gets. With part of the reason why we don't have to worry about idempotence is that the messages are delivered in order and exactly once. Okay, so these are separate TCP/IP connections on each of these wires that are shown in the diagram is a separate socket. Okay. Yeah, so the problem here is that these 2 account managers are both maintaining as state variables their own view of the balance. Okay, now in this web interface, I can't easily make two transactions be close to simultaneous. Okay, but in a distributed system, they could be occurring very close to one another. And there's delays in the communication. And consequently, these two account managers may handle these deposits and withdrawals in different orders. And one of them may choose to reject a transaction that the other one accepts, in which case the two account balances will get out of sync, and you don't have eventual consistency, right? And the reason for this is that I have no semantics to the ordering of events, and the updates to the record are no longer ACID 2.0. And so this is not going to be very acceptable. Now, I created a version of this program that, it replaces the WebSocket servers with just a little simple program that just rapid fire produces transactions. And in this little test case, the two sources of transactions are both periodically issuing requests for transactions. And in particular, the first one, every 1 second is depositing $100. And the second one, every 2 seconds is withdrawing $200. Okay. So if everything is ordered just right, an overdraft should never occur. But everything doesn't get ordered just right. And so overdrafts occur non-deterministically. If I run this program, okay, I'm going to see overdrafts sometimes. Yep, okay, here. So interestingly enough, both of the account managers saw the same overdraft, and consequently the balance is still consistent. Okay, but that is an artifact of the delays on the network communication. So if I run this repeatedly, I'll get a different behavior where overdraft detection might occur at a different place. And again, it looks like both of them saw it. I think on my machine, the network latencies tend to be pretty deterministic. So you get a little more repeatable behavior than you would in a distributed system. But hopefully you can see that in general, you have no assurance of consistency, right?
Well,
this is the notion of consistency.
The only way to make that stuff really work in a distributed system, though, in my mind, is to have tentative operations which reconcile after a while. And the definition of reconciliation is some notion of increasing durability. It kind of stuck over time.
Yeah.
And that typically requires, I don't know yet, but I know after a while when things, and there's all these weird anomalies that people do in real business. It's just, distributed state is not the same as centralized state.
I agree.
That has to be wrapped into what the behavior of the interactions are.
Yep. There's another approach to this, however, which is the approach that I'd like to talk about here, okay, which is to give a meaning to the ordering. Okay. Give it a semantics. I mean, I think what you just described is don't give it a semantics. Just make sure that something happens and that everyone agrees on what happened.
I don't mind what you're just saying, where you're going. I don't mind at all.
Okay, good.
I'm not arguing with that.
Edward, one question. Like
Yes.
something happened versus something specific happened. Like let's say every one of these nodes, they are like, it's not like they just do one operation. They do a lot of, like let's say on that kiosk, you have multiple requests. They're sequential. How would you determine like the logic is like now holding at the latest, because these are very dynamic as they go through.
Yeah. So the approach that we take, and this is sort of the central principle in Lingua Franca, is to give a semantics to the ordering of these distributed events.
Mm-hmm.
Okay. And then a correct implementation of the program is one that respects those semantics and handles the events in that semantic order. Okay. Now I'm going to show you that you can't always do that. All right. There's fundamental reasons why you can't always do that.
Yeah.
And so you have to be able to detect exceptional conditions where you're unable to handle events in timestamp order. Actually, that's not quite true. You can always do it. You can guarantee that you process events in timestamp order, but you'll pay a price in availability and in robustness. If components fail, then things will fail. But I'd like to walk through some examples that actually illustrate these points.
Yes.
But there's one perspective, which I'm pretty sure you agree with, Edward, that you can have observations by each of these participants about events they've observed so far, and then they can generate events that are predicated on what they've observed so far. There's kind of these, event horizons of observations and responses to those observations. And the question becomes, when does the business logic cause them to collapse and coalesce?
Right. So you're getting way ahead of me, because that's what I'm going to show in this accounts 8 program.
I'll shut up longer. Good. Keep going.
Okay. So I'm going step by steps here. So the first thing that I do is, in order to give a semantics to the ordering of the events that are delivered to the account manager, I no longer use this squiggly line, which throws away timestamps. So now timestamps are actually used. Now, a couple of things about the Lingua Franca environment is that in order to use this decentralized coordinator, and only for this decentralized coordinator, I have to do some clock synchronization, okay, across the distributed system. If I don't do any clock synchronization, I can't really use this decentralized coordinator. I have to use the default coordinator, which is much more heavyweight, okay? But because I do clock synchronization, I get a very, very efficient execution system, okay? And I'd like to show you that. So first of all, for clock synchronization, by default, Lingua Franca will provide a software-based clock synchronization mechanism that implements the Huygens algorithm, which we've talked about before in this venue. And it's because it's not relying on any hardware support, it's not particularly precise, but our experience is that it does a pretty good job. It gets clocks synchronized across distributed systems, well, on a local area network down to a few tens of microseconds. On a wider area network, it's sloppier, but it's better than NTP, okay? But you can also turn it off and use your own clock synchronization mechanism. Now, so let me walk through a little bit about what this simple WebSocket server does. So this simple WebSocket server is a reusable component that has a reaction that at startup just sets up the WebSocket to listen for incoming messages, okay? And whenever an incoming message comes in over the WebSocket, it schedules this thing that we call a physical action, which is a timestamped event. Okay, so it'll draw that timestamp from the local clock. And then it'll have a reaction to that event that simply formats the message as a string and sends it out over the WebSocket, sends it out over the output port, right? This is a message coming in over the WebSocket. So this is a deposit or a withdrawal coming from the browser, all right? The timestamp gets assigned here. Once the timestamp is assigned, then the semantics of the program is that both account managers should handle events in timestamp order. All right. So you've got an ATM machine in London, an ATM machine in Singapore. Their clocks are loosely synchronized. If you get near simultaneous events, you will get timestamps that are close to one another. But now there's a semantic meaning to the correct order of execution of these transactions. Okay. If the clocks were very poorly synchronized, this semantic meaning wouldn't be that useful, but it's still a semantic meaning. Okay?
You're adjudicating between the ambiguity of which one comes first.
Exactly. And you're simply giving a definition for what is the correct order of transactions, and consequently now there is a semantics to whether an overdraft occurs. Okay, whereas with the non-deterministic Hewitt-Actor model, there is no semantics to whether an overdraft occurs, and it's going to be a complete accident of, and even a database transaction schema that just does stuff in encapsulated transactions, but those transactions commit in non-deterministic order. There's no semantics to whether an overdraft occurs. It's an accident of the network and everything else.
But you still have to adjudicate about whether an earlier timestamp that got stuck somewhere before being received to be processed, whether it is subsequently rejected and whether it missed the deadline. And so there's got to be some notion of rejecting things that missed a deadline.
Absolutely. Again, you're getting ahead of me, right?
Sorry, I'll shut up again.
That was also my question.
Sorry?
That was also going to be my question. What happens if Singapore is offline for a second? Do we know what for them?
Yeah, so I'll get there, but there's even simpler problems that occur sooner. Okay, so I've just started up this accounts for program, and let's go back to my web interface and verify that. Oh, whoops! I better connect. Oops. Okay, connected here. Okay, and you can do deposits. You can do a withdrawal over here. Let's try to overdraw. And no, sure enough, it rejected my transaction. Okay, detected an overdraft, and both of them are remaining consistent. But there's a problem because this particular program has no protection against near simultaneous events, and it's not protecting against network latencies. And consequently, I could have two timestamped events where this account manager doesn't see. So it receives a timestamped event on N1. It thinks, okay, I've got a deposit or a withdrawal. I process it. And then it receives something on N2 that has an earlier timestamp. And now it says, oh, holy shit, I shouldn't have issued that withdrawal because there was an earlier withdrawal that I failed to process because I didn't see it in time. Right? So this program has no protection against that. And so what'll happen now is I can test it up the wazoo using my two interfaces here, and I'll never see the problem, right? Because I can't issue simultaneous requests or close to simultaneous requests. So the test infrastructure may lead me into a false sense of confidence that I've got a perfect design now and everything's going to maintain consistency, but that's a false sense of confidence. Okay, so let's look for a solution. So here's a very old strategy that we could use to handle timestamps in timestamp order. It's called the Chandian-Misra approach, because the authors of this publication are Chandian-Misra, not surprisingly. And this is a pretty old paper, okay? So it's, what's the date on this? 1979, all right? So what this says, what this strategy that Chandian-Misra developed is very simple. It says that if you receive a timestamped event on N1, first of all, you make the assumption that events that flow on any socket are timestamp ordered on that socket. Okay, so Lingua Franca actually does that. It guarantees that an event that follows another on the socket will have a larger timestamp.
Assuming one source and one receiver.
One source and one receiver. It's point-to-point connections with sockets. Yeah. So Chandian-Misra said, well, okay, if you receive an event on N1, you should not process it until you receive an event on N2 with a timestamp at least as big. Okay, so let's
assuming a set of relationships.
Right. So that's implemented in accounts 5. All right. Which is the program looks the same. All right, but it's got slightly different logic. It's the way that it is implemented in Lingua Franca is actually very straightforward. The two account managers set a parameter which is called somewhat cryptically STA, which stands for safe to advance. Mm-hmm. Okay. And what this means is that when the account manager receives an input event, okay, with a timestamp, it is safe to advance to that timestamp only after waiting forever. Okay, that's what this says.
Implicit in this is you have a bounded set of participants. They're pulsing a timestamp at some level, and so everybody can advance time when they know everybody else's advanced time, so they can see previous things.
Absolutely. So, I mean, this is it's not going to come as any surprise. This is not going to be a very satisfactory solution, right? But let's run it and see what it does. Okay, so I start up accounts 5. I go to my user interface. I connect in the 2 places. Whoops, keep doing the wrong thing here. Right, I'm connected. So I deposit $100. What happens? Nothing. No balance in either place. Okay, so let me withdraw $80 here.
You could have a semantic that deposits don't have the ordering constraint because they're not going to blow up.
You could. That would be another variant. Actually, that would be accounts 9 because I didn't do that here. But anyway, in this case, so I just deposited 100 here and withdrew 80 here, and it's reporting a balance of 100, and that's because it hasn't processed the withdrawal of 80 yet, which is it's waiting for an event from the other guy. Now, of course, one thing that I can do, and Chandy and Misra pointed this out, is I could send a null message, just do a deposit or withdrawal of 0, and then I get an update, and both places end up. And as long as both of these guys keep sending zeros periodically,
that's the heartbeat.
Right. Yeah. So you could modify this program to do a heartbeat, and in fact, I've done that here in account 6. Okay, so here the server has this little Lingua Franca clock, which says every 1 second, invoke this reaction. And what this reaction does is, well, it says, if I don't have anything from my local user interface, just send a 0. So once per second, it's going to send a 0. So if I run that version.
And now you've proved May correct.
What do you mean?
Now you didn't need time at all. I guess the worst case latency is assumed to be forever, if that's what the intention of that is.
Well, you're still
simulating time.
Yeah, but you still need time because we're using time for the semantics of the ordering now. And we're guaranteeing, in fact, in this case, that we are going to process the transactions in timestamp order. And consequently, we're going to maintain consistency.
You are and you're not, because the timestamp order is actually the heartbeat received order. And it's the consensus of the heartbeat received.
No, these are not connected. The heartbeats are, again, the channels here are in order reliable delivery, TCP/IP. Okay, so the heartbeats come in order, and they have increasing timestamps. So timestamps are guaranteed to be handled in order. So I can do any number of transactions. They can be close to simultaneous. They can even be actually simultaneous. Makes no sense in a distributed system, but semantically, it just means they have the same timestamp. Okay, and so this works, and in fact, it maintains consistency, but at the cost of having to send these messages, these heartbeat messages periodically. And of course, it's also not very fault tolerant because.
But do you just mean sequence numbers, like monotonically increasing sequence number rather than timestamp?
There's no difference between those, but well, there is slightly because we have we also synchronize clocks, and the reason for that is because we think that there should be some semantic meaning. If you do a deposit in Singapore that is noticeably earlier than a withdrawal in London, you should honor the deposit. And if you're just using sequence numbers, there's no guarantee that's going to happen.
Edward, is there a mechanism that looks for, I mean, you're probably all going to be also limited by the Cal theory.
Yeah.
That looks for basically if your clock delivery system is lying or has some problems or.
Yeah, you're a perfect straight man, Ahmad, because that's what I was just going to point out, right? Which is there's a fundamental trade-off here. This system actually guarantees consistency. So the C in Cal is consistency. The L in Cal is latency. If network latencies get large or the network fails, which means the latency goes to infinity, then the Cal theorem says you're going to pay a price in availability.
Yes.
Okay. So we can actually do this. So this thing is still running, right? So let me whoops. I'll get a new window here and find the process names. Okay, so here are my the processes that are running are the two account managers, A1 and A2, and the two web servers, W1 and W2. So let me kill one of the web servers. Let's see, the process ID is probably this guy. Okay, so I've killed one of the web servers. I'm not sure which one. I think it was W2. I'm going to guess that this is W2. Yeah, this one is disconnected. Okay, so Singapore just dropped out. So now I attempt to do a deposit. Oh, haha. I forgot that there's a very nice feature in Lingua Franca that when a socket gets broken, it treats it as this guy vanishing from the program. And that gets modeled as if a null message with timestamp forever got sent. And so now the input is actually known to be absent for the remaining execution. And so it actually is able to continue processing.
It just got removed from the well-known set of participants.
Yeah. But on the other hand, if the socket had not gotten disconnected and the delay had simply gotten very large to an hour, say, then in fact, when I do the deposit on the other one, I wouldn't get a response for an hour. So this is the fundamental Cal theorem trade-off, right? If this design is maintaining consistency, the latency, if the latency goes up, the unavailability is also going to go up. Okay.
So I have modeled this by setting a sig stop to the process instead of a sig term.
Sorry?
Could I have modeled this by sending sig stop to the process instead of sig term?
Actually, that's probably a good point. Yeah, I could have done that way and just kept the socket open. I would have to keep the socket open for Lingua Franca to actually not to actually block. Yeah, but in any case, this solution, although it works and maintains consistency, is not really that attractive because it's not very robust, right? So let's look at another possible solution. So in particular, let's look at the solution that is implemented in Google Spanner, okay, which I think everyone here is familiar with, all right? So Google Spanner also uses timestamps like this. And Google independently reinvented a technique that we had published 5 years earlier. This is our paper from 2007. We were proposing the use of this technique for cyber-physical systems, whereas Google is obviously using it for database systems, which is really quite different, but different application, but same technique. Okay, so let me explain what the technique is. And to do that, let me go back to the Lingua Franca program. I'll go to Accounts 7. Okay, and this one is really only slightly different from the previous one. It sets the safe to advance threshold to 30 milliseconds. Okay, what does this mean? Well, this means that when the account manager receives an input here with a certain timestamp, it watches its local physical clock. And when its local physical clock hits the value of the timestamp plus 30 milliseconds, it processes the event. Okay? So what this is doing is guaranteeing an unavailability bound of 30 milliseconds. Okay? This account manager will always respond within 30 milliseconds to a query. regardless of what the other guy is doing and what the network is doing. So because it's guaranteeing a bounded unavailability, there is the possibility of an inconsistency. The Cal theorem tells us that that is absolutely unavoidable. You can't get around it. If you bound unavailability, you have a risk of inconsistency. Okay. And how would the inconsistency occur? Well, if the account manager receives a timestamped input, waits the 30 milliseconds, then processes it, and then later receives an input that has an earlier timestamp, then it may be processing these events in a different order from the other account manager because it didn't process them in timestamp order, and therefore you get an inconsistency. So what Google Spanner does is that, they first of all synchronize, they use, dedicated trunks to connect their data centers. So they have a globally distributed system, and because they're using dedicated trunks, they have much more control over the network latencies. They collect statistics on what the network latencies that they're actually getting, and do some number of nines assurance about the latency. And then they also run their own clock synchronization schemes. So it turns out that in this case, you can't tell the difference between clock synchronization error and network latency. So if the clocks are off, that's just as bad as having a bigger latency. So the L in the Cal theorem is actually an apparent latency. It's a measurable latency that incorporates not just network latency, but also clock synchronization error. Okay. So if you can guarantee that the
I have a
latency
question, Edward, just a clarifying question.
Yeah.
When you refer to latency, are you referring to the one-way latency or the two-way latency?
So it's the L in Cal is a one-way latency, but it's actually not the physical one-way latency, which is an unmeasurable quantity. We call it a apparent latency. So when an input arrives with a certain timestamp, the apparent latency is the difference between that timestamp and your local physical clock, something that's easily measured. Okay? That's the L in Cal. It's an apparent latency. And that will include clock synchronization error.
And that includes that's all done on a single timeline on one machine. You're measuring that one-way latency, effective one-way latency on each local timeline.
Right. Each machine is using only its local clock for physical time. And then timestamps can originate elsewhere, but and so the timestamp may be originating from a different physical clock, but it's you only ever access physical time on your local machine. You can't get it anywhere else.
Thank you.
Okay, so that's this safe to advance offset bounded, but now the question is, well, how should you deal with the possibility of an inconsistency here? If you can guarantee that your apparent latency stays below 30 milliseconds, you'll never get inconsistency. But nobody can ever guarantee that completely, right? That's not practical in most distributed systems, right? So let me go through some notes here. So when the assumption of 30 millisecond latency is violated in Lingua Franca, we call this a safe to process violation. Okay. And in the Lingua Franca program, you can put an exception handler that will be invoked when you are processing things out of order. Okay. Now I have a student who's working with me who has proved something that I think might be new, which is that eventual consistency is possible if and only if the merge operation is commutative, associative, and idempotent. Okay. I always knew that the if was right. If you have ACID 2.0, you get eventual consistency. He's proved actually that it's not only an if, it's an if and only if. So eventual consistency implies that your merge operation is commutative.
That is the implied definition of eventual consistency, is that it means they're isomorphic.
Yeah, exactly. So we have a very elegant proof of it. This may not be new at all, but I've never seen such a proof of this. But anyway, but that says that we need to find a way to make the merge operation commutative, associative, and idempotent in order to guarantee eventual consistency, even if our assumption about network latency gets violated. Now,
as they just pointed out, you should look at the Calm conjecture and the Calm theorem and what they've worked.
That's the basis for this. So what all that he did was, in fact, so the Calm paper is a little too hand wavy, right? The definition of eventual consistency is a bunch of words that have multiple interpretations, and it turns out that you can formalize this notion of eventual consistency as a monotonicity requirement on a mathematical function.
But as you pointed out with your time stuff, right, you want to say what didn't make a deadline. And then the confluence that the Calm conjecture talks about, there's no deadlines imposed, so you can't actually, they talk about does exist observations versus does not exist observations, and does not exist requires that time got capped in some way or another. And so, one way of reasoning about that is to add a quorum or some form of subset of the reconciliation so that the deadline can be advanced without waiting for every single server. And I talked about that in decoupled transactions in CIDR 2022 about what it means to say, no, this didn't make it. I've got a subset of the nodes that saw it. I've got my quorum. And so things aren't going to stick. But you now have to define the transition to tentative to is going to stick, and that transition of the semantic. The other piece of the puzzle that you're not identifying here is you're assuming read-write semantics, which doesn't open up a behavioral operation of what it means. And so those are things to pop into how do we interpret the behavior of commutative?
Yeah, I agree with everything you just said, and I guess I would point out that there's actually many different ways of dealing with this. I mean, the way that Google Spanner deals with it is by overlaying a layer of transactions on top of this. But one of the things that does is it does give you the atomicity of the updates, and it does give you consistency, but it loses the semantics of the ordering. So you don't necessarily process events in timestamp order in that case.
No, but the database stuff doesn't formally do that. It talks about what did I see before and what do I see after. And so it maps it to a classic database perspective, which is limited in its own ways.
Right, exactly. So in a database context, I think that's a perfectly reasonable solution.
They were trying to do.
But in the kinds of systems that I'm interested in, cyber physical systems, it's not always a reasonable.
No, you want to assign a behavioral thing that has a looser reordering ability to give correctness under more circumstances.
Right. So one way to accomplish this is actually a rather old technique. There's a whole family of variants of this, but this dates back to 1985. Okay. Where Jefferson introduced what he called time warp. And this was simply speculative execution. So what you do is when you receive an event that is out of order, you backtrack to earlier than that event, restore your state, and then play back the events that you've seen since then.
It depends what playback is.
Is this like we call it like the dirty right?
I guess you could call it that, but I've not heard that.
Like you basically proceed with whatever you have rather than waiting for the dust to settle, that STA. But then you have a way to go back and fix things if they were wrong.
Yeah.
And then you proceed. You proceed going with some buffers.
Yeah, that's what it is. So the problem with that is it's really hard to roll back the ATM spewing out cash.
Yes, of course.
But the reality is that banks made this decision since the 70s and 80s is if the person standing in front of the ATM on the side of the bank at 2 a.m. can't control the disconnection, they can't game the system. If there's a rare case where you give them $200, it's a cost of business. And so many of these things are factored into the behavior of businesses that our academics don't care about.
So that's exactly my point, right? Which is that there's many ways to deal with this problem. The interesting thing that I find is, well, how do you build the software to implement a business decision?
Yes.
You get to know programming language people.
Yeah, but this is what we do in Lingua Franca, right? And so let me give you what I think is one possible solution, business solution, okay, which is represented in this Lingua Franca program, okay? So here we have an account manager that uses this bounded 30 millisecond behavior, all right? And it will give you a guaranteed response of 30 milliseconds. If you withdraw $100, it'll give you the cash within 30 milliseconds if the local view of the bank balance is sufficient, period. Okay, so you guarantee an availability of 30 milliseconds. But you really need to be able to maintain long-term consistency. Otherwise, these things could get out of whack with one another and stay out of whack. So here we have another component, this balance component, which is using effectively the Chandy and Misra technique. Okay, so it guarantees a consistent balance. So we've got two replicated versions of this that can be across a distributed system. And it uses heartbeats to ensure that these things are maintained within a reasonable amount of time. Okay. But there's an availability cost, as I pointed out to you before, right? Because of the Cal theorem, the true balance can't be known necessarily within the 30 milliseconds. So you don't want to block the account manager because you have an availability requirement, but you do want a true balance. And you want to be able to correct the state of the account manager with the true balance every once in a while. I mean, this is actually what banks do. They reconcile their accounts, it's like once every 24 hours. All right. So what we do here is sort of a very limited form of the Jefferson time warp, which is we send the true balance back with actually a timestamp offset. And what this timestamp offset does is it says it's really okay with me for the account manager and the balance component to disagree over a bounded region of the timestamps. This is a bounded inconsistency.
Bounded, yes.
Okay. And in exchange for this bounded inconsistency, using this true balance doesn't undermine my availability.
Okay. All of that is what I was trying to bundle into memories, guesses, and apologies.
Right. Yeah. So this ability to insert a bounded inconsistency and use that to get better availability is exactly what this software framework lets you.
There you're remembering what really did happen and cat herding it together over time. Exactly. And then realizing there's apologies, and you figure out what are you going to do when you've screwed it up, and that's fine because it's more cost effective for business than saying, no, I'm going to be perfect, stop.
Exactly. And so this also fits in. I mean, I think you've expressed this beautifully in the past, Pat, which is that the account manager knows what you knew in the balance, not what you know now, because knowing what you know now is too expensive. It costs you in availability, right?
And so this is really revamping some of the common knowledge stuff. And I love what you just said. And I'm reiterating it. I don't know what you know. I know what you knew. And if I can cat herd the past with which you knew, then I can reason about that uncertainty window.
Exactly.
So, Edward, I have a question. Can we put this semantic ordering in say, an FPGA in the SmartNIC?
Yeah, I think that has tremendous potential. And I think that one of the nice things about, working at the networking hardware level is that these 30 millisecond assumptions could be really tightened up and actually guaranteed with, some number.
Nobody needs to know high traffic trading crap. None of that, because we've got money with it.
Right. So this is what some of the exchanges have exactly rolled out. One of the major network vendors added a feature called wire order delivery for doing exactly this.
Yeah. Yeah, exactly. I mean, in fact, when I showed you the 2007 paper, or when we first developed this technique using these safe to process offsets, at that time, one of the sponsors of our project, which was HSBC, who were doing, it was a particular sub-organization within HSBC that was doing currency trading. And they were very interested in this distributed mechanism based on timestamps for doing arbitrage with currency trading. And so that it's clear that there's application of this to financial transactions.
Well, those currency trading people are also doing betting. And so the question is, if I'm going to have a tight time window and I bet and then I lose and it's rare and I can do the math, then I can figure out that I can still make money on it. That kind of.
So anyway, I'll stop sharing here, but this, the point here is that you really need a way to build in these kind of business choices subject to the fundamental constraints of the Cal theorem. And I've been finding that this decentralized coordinator in Lingua Franca gives me all the knobs I need to turn to get so many different variants of these business decisions. And so I'm really kind of liking it. But
I really like your graphics going from the program text to the graphics are cool.
So a quick question, Edward, like what's the relationship between like this logic, I mean loosely, of course, like this logic as you move forward and let's say quote unquote blockchain?
So that's a very good question. So blockchain is basically has sort of a fundamental requirement for a strong form of consistency.
Exactly.
It's quorum based, right? The consistency is developed by a majority of participants. And the use of a quorum-based definition of consistency is the way that they mitigate the potential unavailability.
Exactly.
Right? They don't need perfect consistency across all participants.
Switching the number of nines to get consistency, you're adding a lot of nines.
Yeah.
Right. So they just need a majority, and that's another business decision that you can make, right? So you basically change the way you define what your true actual value is at a timestamp.
Yeah.
And that in the case of blockchain, it's based on a majority vote.
But to me, blockchain creates an image of the past. It's a provenance of what we've observed and has happened. And then you can find what makes it into the blockchain predicated on the quorum, which is comparable to what I've been saying earlier.
Right. Well, the Cal theorem says that any distributed agreement is an agreement about the past, right? Because unless latency is zero, right?
The quanta is different. Like over there, the quanta is determined by some ticking of some like clock, a physical clock, but then in this one is like a logical step as they move forward.
They're isomorphic.
Yeah, isomorphic. Exactly.
I do want to jump in and point out that blockchains don't have a majority quorum notion.
I didn't think so either. It's just whoever certifies what they saw. But if you view it as different people's observations coming together into one history, then you can superimpose that, I think.
Why is that majority, May? Why?
It's a majority in the sense that if you want to cheat the blockchain system, you need to have more than half of the participants cooperating.
So just the end of that quick explanation for you. The purpose of the blockchain system is to give the miners a puzzle that causes them to slow down so much that with high probability, no one is going to send a new block out simultaneously with someone else, where simultaneously is defined as just overall the internet happens to see this traffic. The concept is that people are extremely well motivated to send their blocks out as quickly as they can, and that if no one is colluding, they will get that block to the rest of the world in time for the rest of the world to make their own local decision that it's better to build on the block they've received than to try to race it, given that the other block has a head start.
Just nomenclature, May. I think a blockchain is the adjudication of the past, which is separated out from proof of work that Bitcoin does. But I'm thinking of it wrong.
No, I posted a few links too. There's different mechanisms depending on the blockchain. Some are switching from proof of work to proof of stake, where basically whoever has more money gets a larger say, and then there's other mechanisms too.
But there's a differentiation between what happened in the past, which may or may not have stuck, and what did we decide to stick.
But the thing they all have in common is some reason why we expect a small number of blocks to arrive in a time window, and for it to be clear which block's the one that really should win, even if the majority of the participants are offline for that time.
Yeah, but that's about adjudicating the future as opposed to remembering all the crap in the past. That's all I'm trying to take apart.
It's like something that we should pick up and have a much longer conversation about. Now, next week, we've got David Lariviere leading a discussion on HFT. And maybe, David, you could include this conversation about blockchain then?
That would be a nice transition, yes.
Blockchain, full disclosure, not my area of expertise.
But we can bring in people who would want to hear this conversation, especially that the comments.
Yeah, but David has some stuff he had lined up to do, so maybe you don't want to take his time away.
Okay.
I'm happy to be shuffled around. The one other question I did want to raise, though, is this discussion of we can't measure one-way latency. I'm curious about that because we do that in HFT. We have these very fancy, I think it's like a $400,000 device that can get you micron level accuracies one way of the latency. And I think there are even other devices that are like femtosecond level synchronization.
Right. If you put the two boxes next to one another, and your network is a coil of cables, you can measure one-way latency. Clock synchronization people do this all the time. The problem is that when you have two devices that are separated by many kilometers, you can't run your oscilloscope probes many kilometers. I mean, it's, you sort of have a communication problem.
These aren't based on measuring at both ends. It relates to setting a pulse and getting the reflection back. And so theoretically, you can even do this continuously across continents, for example. I think there was some work out of Europe, some of the labs.
But that's measuring round trip latency. If you look at the theory of relativity, it actually works fine if the speed of light is different going north than south.
Yeah.
And physicists generally assume that it's symmetric, but there's nothing in the theory that requires it to be.
Exactly.
And so there's actually you can't even define what you mean by one-way latency. It's not a sound concept in physics.
One thing I want to add, David, sorry, Edward, is I'm just wondering in terms of methodology. All of these methods I see that you start from just for sake of not having the right word or terminology is you start bottom up. You start from blocks that are independent and you put them together to create a bigger like system or accumulation of everything. I look at things a little bit different. I look at them from top down, where in top down you are trying to virtually create like this illusion of presence. You're trying to basically make all these machines one big machine, but now it happened, you don't have enough resources, so you have to break it in pieces, and they are distant, so you don't have instantaneous communication. You don't have that presence of the clock, or like the thing that we always teach people in distributed systems, that there is no common clock, and deal with it. So what if you have, let's say, in your block, again, just this theoretical, what if you have, again, quote unquote, entanglement, where you have, let's say, a register with another register entangled. Wherever you put something in this, you have it in I mean, this is a loose definition, physics people, sorry. Let's say you put in this instantaneously in the other register, you have the same value. And then let's say you have also a monotonic increase in another register that is exactly the same thing everywhere across all your system. With these tools, would you rethink or put, let's say, this whole architecture in a different way?
So, yeah, if I could do magic, I would certainly rethink the whole architecture. But I can't do magic. And in fact, entanglement doesn't give you instantaneous communication. That's a basic.
Yeah, I know. I'm just lying to myself.
Yeah. And I mean, there's this wonderful conundrum that is triggered by Bell's theorem, right, in quantum mechanics, and it says that if you accept the principles of quantum mechanics, you have to give up one of two principles that physicists hold dearly, right? One of them is called locality,
exactly,
and so one way to reconcile the conundrum is you can say, well, actually instantaneous communication is possible somehow. We don't know how to do it yet, but Bell's theorem, that would resolve the conundrum. But I think if you believe relativity, you know that that's not the case. And so you're stuck with having to give up the other principle, which is sometimes called reality.
Yeah.
And the principle of reality says that if you make a measurement of a physical object, that the results of your measurement are ultimately determined by the properties of that object. And you have to give up that principle. And what that means to me is that if you talk about a physical system, that a physical system doesn't have a state.
That's right.
Okay. There's no physically sound notion of a system having a state. And it's particularly noticeable in distributed systems.
Mm-hmm.
And this is what makes them so hard to reason about. You can't say, what is the value of this register and this register at the same time, because you've imposed on this system a notion of a state. But actually, if you insist on imposing that, you're going to have to give up locality according to quantum mechanics, and you're then going to be able to do instantaneous communication.
This is why my friend David Longbeard, who departed a few minutes ago, is a happy person, because he fundamentally believes that all of the universe is a cumulative distribution probability function of probabilities of outcome, and he's at peace with that.
Yeah.
It allows him to sleep at night.
Yeah, that's one way to deal with this in practice, is to just accept uncertainty.
Mm-hmm. That is what I'm saying, and I'm pointing out that you're right at that level. But there is a way of reasoning about it philosophically too.
Yeah.
Yeah, I'm curious on your thoughts. Again, strictly based on ChatGPT, if you're doing OBR at both ends, I think you can correct for relativity.
What's OBR?
It's the optical backscatter, where you're sending a signal and you can basically measure the round trip at every single point in the cable. You can see the individual passive taps, joints, etc. It's how we get extremely, extremely precise measurements. When people are terrified, they're at a picosecond disadvantage, which they still will be. But
so in a previous life, I actually did communications theory, and one of my most cited papers is one about free space optical communication, and this is complete news to me. I've never heard of this.
Well, free space, you can't. This is only in a fiber optic cable. Free space, you can't do this. You're taking advantage of basically being able to bounce signals off different portions of the fiber optic cable. And then in this case, really extreme, doing it from both ends.
This is like time domain reflectometry, but on a optical cable. What you're doing is you're measuring everything, just like the dislocations you measure in any transmission line. Plus, you also have to deal with the backscatter, which is the Rayleigh scattering. That's how I understand it.
I suspect
putting on my Longbeard hat, I would just say sure, but you just got a shit ton of nines.
Well, I would also say that I mean, you can't violate a basic physical principle, which is that one-way latency across a distributed system is not a well-defined concept.
I'm
measure something that isn't well-defined. So I suspect that if you drill down into this, you're just measuring a bunch of little round-trip latencies.
Yes. I'm in conversation with Geraint Lewis about this, and he's literally the world expert on this particular problem. He was the one who inspired the Veritasium video about the one-way speed of light. So we could bring in Geraint. Unfortunately, he's in Australia and he's on the wrong time zone. It's the middle of the night for him. But maybe I can persuade him to come in on one of our sessions, coming in the middle of the night, just like Ahmed did when he was in Japan. All right, I'm happy to go on a little bit longer, but I just wanted to let everyone know I was very lax on pointing out we're at the top of the hour. We've had some great discussions. It's drifted off into some other areas. What I'd like to do is basically say, let's close down this meeting, and I'll add those as agenda items for future meetings and try to bring in some experts like perhaps Geraint Lewis into these meetings. Next week, David Lariviere is going to be leading the discussion about time and causality and high-frequency trading. Unless David comes up with another title before then.
I'm sorry to miss that. I'll be somewhere over Greenland at that time.
Before we go, I just wanted to quickly jump in. Sorry for interrupting folks, and point out, just to circle back on the COM result. So there is a much more precise proof of it, not from Berkeley, that I put in the chat.
Oh, so, great. Thank you.
Yeah, I want you. Yeah, look for messages from me in the chat. It's from Amalut from 2015 or so, and it's a precise characterization of both directions of the theorem.
It is, and they've been cited in the recent papers in the Comtheorem. They point out that there's been proved by the folks in Amsterdam and Netherlands.
I don't see anything from you in the chat. Oh, no.
I'll send it to you again. Give me a moment.
Is this the one you sent at 9:54 a.m. Chicago time?
Yeah, I've sent it again. So now
I got
now,
it. I got it. Great. Thanks.
Sure.
Thanks, everybody. It's been fun.
Excellent discussion. Really
See you
good.
later.
Thank y'all.
Goodbye.
Bye, everybody.
Next week, same
Bye,
time,
everyone.
same channel. Thank you.